Okay, so next class is indeed an exam.
Right.
So, in fact, it's the only exam. Because the final is a project in which you give a presentation. So along those lines, you should be figuring out what topic you'd like to talk about. There are a bunch of topics listed in the syllabus. You can certainly pick one of those or come talk to me and we can negotiate a topic for you to talk about. General idea is it's going to be basically a paper or something like that, but it doesn't have to be. So let me know, and if you want to discuss over email, if that's more convenient, we can do that as well. But I'd like you to be starting to think about that now so you've got ample time to prepare. Because I don't know about you, but it takes me about a week to prepare a 20-minute talk or thereabouts, so good to be ready now rather than later. Okay, so midterm exam is coming up, though. That is next class. The parameters of that are 5 questions. They are short answer. You can bring one 3-inch by 5-inch index card, handwritten, both sides. Since this is a computational class, you can bring a standard for function or scientific calculator.
What's a floor function calculator?
Plus subtraction, yeah.
Oh. That's what.
I mean, really, that's only 2 functions.
Right, just to be clear.
So like a TA, what a TA84?
Yeah.
Okay, all right.
Yeah, that's fine. Yeah, I'm not really too picky. In fact, actually, if you manage to program a TI-84 to compute chain complex homology, that would be pretty impressive.
Challenge.
Note to
Challenge.
self. Can that be my project?
Challenge accepted. Maybe. That might actually be fun.
Trying to compute homologies on a TI-84.
Yeah, that would be kind of cool, actually.
But how do you specify the quiver diagram in a TI-84?
Using Pac-Man.
Third side.
Wasn't it you who suggested that I should teach this class using Minecraft?
Yeah.
I actually took the effort to find out there was an open source version of Minecraft out there called Minetest, and wrote a mod or two to see how hard it was along those lines. I get very distracted. Also found out that there was some kind of super TNT as well. That was a lot of fun. Anyway, right, so 5 questions, short answer. Roughly half of them are computational, but not big computations. There's no like 4x4 matrices, they're smaller. And then the other half of them, notice 5 not divisible by 2, but anyway, they're more theoretical, so demonstrate, prove, show, those kind of things. But nothing really super sophisticated. Right, and it's basically class period. So anyway, those are kind of the parameters. What I figured I'd do now is kind of give you a review of what it is that we've talked about, and what would be on this kind of exam. Before we go down that path, I'm going to make questions. All right, then let's do it. Okay, so, right. What did we do topically? So, topically, what did we talk about? We talked about quivers and their representations. I re-emphasize this among other things because they're about to make a reappearance after spring break. And we'll see their evil cousins, the persistence module, but not yet. So quivers and their representations. So things that we might want to do is compute barcodes, diagrams of them, do some examples of that sort of thing. We want to take a look at them and ask whether or not they form chain complexes. Do they chain?
They modifying.
Modifying the representation of a quiver. Do they form a chain complex? And then that leads to the next topic, which is chain complexes. And all the wonderful things that happen with chain complexes, like exactness, computing homology, talking about chain maps, chain homotopies, induced maps, all very good stuff. And once we got the chain complexes in place, then we started thinking about what to do with chain complexes. And we went down the path of the topic of simplicial homology. So we talked about what an abstract simplicial complex is. We talked about once you've got a simplicial complex, you might want to map between them. So simplicial maps. We learned how to turn all of these things into homological algebra and linear algebra. So specifically constructing the simplicial chain complex. And more recently we started talking about simplicial homotopies. And how that interacts with chain homotopies, how that interacts again with simplicial homology. So those are the topics that we've covered really in brief. And the places where one needs to do a lot of computation, well, certainly in barcode diagrams, I'm going to mark with red places where there's computation. Asking whether or not you've got a chain complex, pretty straightforward. You ask about consecutive pairs of matrix multiplications. So yeah, basically this is just matrix multiplication. Check to see whether or not it's going to give you a chain complex or not. Exactness is something that we can certainly have you compute to see whether or not exactness is going to be holding or not. That was done in the first homework, for instance. But really the place is computing homology and computing induced maps. You could certainly check to see whether or not something is a chain complex by doing a whole bunch more matrix multiplication, but that's not really as involved with computation. Now on this side of things, the place where computations turned out to be really essential is in here. Building that sort of thing is not so hard, but then examining that to find whether or not you've got homology, that basically comes back to that other side of the diagram. On the other hand, building simplicial complexes and simplicial maps and whatnot, it's more of a construction rather than a computation. So, generally speaking, on this side is very much typically computation, and on this side is more of a construction. So the effort is in laying out, this is the task that you will compute over here, and over here is actually computing it. Yeah?
How, just in a general sense, how does the computation of the barcode diagram talk to linear algebra?
Okay, that is a very good question. We touched on it a bit,
We did.
and I can review that.
Okay.
And that is the subject of the entire next unit.
Oh, well, okay.
Because basically the point of the matter is, once you have an abstract simplicial complex, you get what? You get a chain complex.
Mhm.
Chain complexes don't have very interesting barcode diagrams. They tend to be fairly short bars. They're not very informative in that regard. And what's really very much more interesting is if I don't have just one simplicial complex, but I got a whole lot of them. And they fit inside of one another in some fashion, like they simplicity map from one to the next. Kind of, how do we get from vector spaces to quivers and chain complexes to the vector space? Said, well, it's all very well and good to look at a vector space or a map between them. That's the subject of linear algebra. Homological algebra, what happens when I string them together and ask about the properties of that? Well, simplicial complexes are all very nice on their own, and when I have a simplicial map, that's all very good. But what happens if I string them along? Basically do the same kind of construction. Now I get chain maps going from these chain complexes. I get this big grid of vector spaces with chain complexes, say, being the columns, and then chain maps being the rows. That particular thing, when you compute the induced maps on homology, you get now a quiver built out of the homology, and we study that. And that's what persistence is all about.
Quiver on the homologies going across
Yes,
one of the rows.
from one simplicial complex to the next.
Oh, okay.
There's a lot of data involved. We'll get there. But the interaction between barcodes and the quivers is merely a matter of how do you understand how the basis of one space fits into the basis of the next space, if at all. And so it's really that's what question a barcode diagram answers,
Okay.
is how do the bases fit together?
And that whole controversy that came up early on, not controversy, but the difficult question early on, where like when you run out of vectors in your basis, you don't have enough to span a space. How do you pick a new
Extend,
one?
right.
Right.
And that particular question turns out to be sort of a red herring in some quivers, not all. The general quiver is a definite problem. In fact, it's an unsolvable problem, theorem.
Oh.
But for specific quivers, those, in particular those that are nice long lines, it's a solvable problem. And in fact, it's an irrelevant problem, and that it doesn't actually crop up. We'll get there, and I think that's not actually a bad place to start in this discussion. Before we do that, any questions sort of about the high level? So from a computational standpoint, what I've done is I've marked out in red the places where I'll basically draw computational or constructional questions, which is, here's a simplicial complex, construct its simplicial chain complex. Or here's a simplicial map, tell me what the chain map is going to look like. Versus over here, here's a chain complex, compute its homology. Where here is a quiver representation. Is it a chain complex, or is it exact, or that sort of thing? That's kind of the extent, yeah.
Do you think that maybe you could send us like a problem or two in that, since we haven't really
Sure.
had homework on that?
Sure.
Thank you.
Sure thing. Okay, in fact, could you take an action to send me an email to remind me to do that? And then yes, absolutely. Okay. Cool, well then I think we'll just sort of get right into it, and I'll start moving sort of forward, and generally the way I try to time these things is that we put some more time into the older things, and then a little less time into the newer things because we've seen them more recently. Okay, here we go. So, first off, what is a quiver? A quiver is basically, it's a bunch of circles and arrows between them, roughly speaking. So, quiver looks like a bunch of dots. and a bunch of arrows. Quiver representation. Looks like something like this. So the arrows have stayed put and the dots have turned into vector spaces, and each of the arrows ends up with a linear map. Each one of those are linear maps. And I'm making the assertion that if you want to get from here to here, and you can do so by following the arrows, you compose the linear maps or multiply them as you go. Okay, so that's a quiver representation. Now, generally speaking, the basis of each of these vector spaces gets, or at least parts of the bases of these vector spaces, gets related to one another by these linear maps. That's what linear maps do. They link up the bases of this space with the bases of that space. That's what they do. Now, they don't necessarily, what's that?
Arrows are-
And the arrows are linear maps, yep. Arrows are linear maps.
Linking bases of vector spaces.
Well, linking the vector spaces, and as a result, they link the bases. And composition is permitted. So if you want to get from one space to the other, if you could follow the arrows to get from one space to the other, then you compose linear maps, and that is the map. So for instance, from here to here, there is a, implied by me saying it's a quiver representation. I've got arrows like that, and I've got arrows like that, and pretty soon things get kind of out of hand, so I don't bother doing it. But I mean that they're all in there. Okay, cool. So, point of the matter is you would like to know how do the bases of these various vector spaces fit together. In much the same way, how do the bases of RP and RQ fit together based on this linear map M. And a barcode diagram tells you how that happens.
How the bases fit together.
How the bases fit together. So the idea, barcode tells you graphically how the bases fit together across the diagram. And key point number 1 is that you get a bar for a bar for each non-trivial basis element. Second point is if a basis element maps to 0, maps to 0, it ends along the way. And similarly, if a basis element maps into something that's already been listed, if it maps already into the basis that thus far, so you build these things bar at a time, and if you map into an area where you've already gotten, then you also end it. So, if a basis element maps into the image thus far computed, its bar also ends. Otherwise it continues. So you build these up in sequence, and then the concern is two things. First of all, you might not cover all of the bases in the codomain once you've gotten there. And it seems to depend on order. It seems to depend on the order of the basis elements that you've looked at. Now, there's 2 points there. You might end up with a not covering the entire image. But bars start. Bars start if they aren't in the image of an incoming map. So you're welcome to extend the basis. And I call this out explicitly because this is something that in your third project you will be doing, is writing some code to extend bases according to this. And then the observation is that the order does matter. The ordering of how you build the bases and which vector space you start on, those matter in general. But not if the quiver looks like so. Or any error reversal above. So if you switch around some of the arrows, it doesn't change the fact that you become order independent. So the concern about order turns out to be somewhat of a red herring in the cases we've looked at. So chain complexes and other such things. Then it doesn't matter. So that's a deep, deep zero. It's not the least bit obvious. And in fact, there are a few others for which the order does not matter that are proven in the same theorem that I'm referring to. And then even recently there were found to be a few more, and that was like a major deal. Like I was at the conference where this was presented for the first time. It was pretty exciting. Okay, yeah.
So hypothetically, say we had a quiver representation like the one we had drawn for 2 vector spaces, 3 vector spaces mapped to 1,
Yep.
mapped to 1, which mapped to 2.
Yep.
Would we write a Barcode diagram for each separate sort of...
Yeah, sort of paths.
Yeah, sort
It
of
basically
paths.
comes along the paths.
Okay.
Yep.
All right.
Yep. And in that case, that particular diagram, nearly everything was like flowing in one direction.
Yeah.
In the case where everything is flowing in one direction, the order doesn't matter so much. The problem is where you end up with loops.
Cyclic, right?
Yeah, some kind of cyclic things. I mean, it's kind of delicate. I mean, you can cook up situations in which the order matters even in those, and it's kind of because even if it's not like a feedback loop, if there's a loop like so, like we've seen these kind of commutative diagrams, that too causes problems. Anyway.
So it has to be a tree?
Even then there's some subtleties. Yeah.
How do you get bases elements? Which one's column reduction?
Good question. All right, let's talk about that. All right. So thus far it's sort of specified in the abstract. Let's talk computational tools.
Like in a quiver diagram, if the basis element dies and we're adding a new one, do we have to send it backwards to see what it was
No,
originally?
follow the maps.
So we can
Yep.
just put it
Follow the
in,
maps.
and it'll still be a basis element
Yep.
along with the original.
Yep, follow the maps. Yep, indeed. Okay. So, tools. Oh, in your algebra, that might be useful. So, we've got such things as a matrix, let's say. We've got a matrix. let's say I've got a matrix that looks like this. Matrix L goes from Rn to Rm, so it has
M columns and M rows.
M rows and columns. That's the shape of the matrix. So Python here, L dot shape equals,
Is Python on the exam?
no,
Okay.
nope, I'm just being unambiguous.
All right.
No. Or in MATLAB, similarly, instead of shape, the size. So that's Python. Okay. Okay, right, so that's this matrix. So now what can you do to this matrix to understand different properties of it? Well, you might want to know its image, and you might want to know its what's in its image, you might want to know what's in its kernel, what's in its co-image, and its co-kernel. The 4 fundamental subspaces. So you can think of, there is a way to transform the domain and a way to transform the range. So a way to transform the range and the domain so that it looks like something like this. We call this one P and this one Q. This is going to be L prime. And the point is that L prime is, what is it? It is Q inverse L prime P. That's a coordinate transform. And generally speaking, you do this whenever I can invert Q.
So L is equal to Q, not L prime is equal to.
Yes. So, this way. And this is not showing the 4 fundamental subspaces, but if you're careful about choosing P and Q, you can write it so that you get a very special form. You can break up your Rn, and you can break up your Rm. So the Rn is 2 pieces. There's the kernel, and there's the co-image. And then this is the image and the co-kernel. Break it up into these 4 fundamental subspaces.
Is the code image the image of the transpose of?
Indeed it is. Indeed it is. Yes, the co-image is the image of the transpose. The co-kernel is the kernel of the transpose. The image and the kernel are what you think they are. So the kernel maps to 0 in both L and L prime. The co-image, where does that go? Where does the co-image go? Well, the kernel mapped to 0.
The co-kernel?
Nope.
Is it the row space?
Well, so say this maps to
0.
0. This maps to where? Well, there's only one place it can go. It goes to the image. The co-image maps to the image. The co-kernel, it would be the kernel going the other way, so it never touched. So in particular, reason why I drew it this way is in the barcode diagram, you're just really showing this top arrow. This is the bar. This kernel is a bar that ends partway through.
So the bar is the map from the co-image to the image.
Basically, the bar is the map from the co-image to the image. That's right. There's a collection of bars, however many that you've got in the co-image, which is the same size and the same number as the image. That's the point. Kernel, everything got mapped to 0, so the bar ends. The kernel here, that's all stuff that wasn't in the image, and so these will start new bars. So the co-kernel starts new bars. and the kernel, they all add. Okay, so now let's turn this into row and column reduction. Okay. So when you look at the output of L, what is it doing? Well, the matrix interpretation is a useful thing to think about. What does the matrix interpretation tell me? Well, every column of L is where in these four fundamental subspaces? If I grabbed out a column of L, where would that lie? Well, yeah, so if I grab out a column, that is in Rm, grab out a column, Rm, and so where does that lie? Well, one of these two subspaces, right? Which one does it lie in? Well, it doesn't lie in that one because that's not in the image, so it's in here. So each of the columns of L lie in the image. So, each column of L is in the image of L. Okay? Now what about each row?
Is that after reduction?
Oh,
So after mapping, it becomes,
well, yes.
yeah.
Yeah, I mean, so it's the image of which vector? Zeros, a 1, and then a whole bunch of other zeros. So that's clearly in the image. So that's after mapping through L. That's really the thing that you need to know. So what that says is if I do column reduction, am I changing the image? I'm just taking linear combinations of things already in the image. So I never change the image. So, column reduction of L preserves the image. And, in particular, finds a nicer basis for it. Reduces it from a spanning set, removes all the redundancy, and eventually finds you a basis. Now, dually, what does row reduction do?
Gives you the coverage of.
Gives you the co-image, that's right. Row reduction of L. It's going to do something, it's going to, every column was, my hands are wrong, every column was an element of the image, every row is an element of the co-image. Because that would be the image of the transpose.
The difference between a co-image and a column and a row space, or?
No, there's different names for the same thing.
Oh.
This is the less computer sciencey way of saying it.
Okay, I was reading Lay over the weekend.
Yes.
Yeah. Okay.
Yes. Yeah, row reduction preserves the co-image and finds a nicer basis for that. Now, in particular, row reduction preserves the kernel. But we're preserving just this side of the diagram. Row reduction will change the image. It changes not the dimension of the image, but it changes the basis. Similarly, column reduction changes the basis for the kernel and the co-image, but not the dimension. So beware. If you're looking for the image of a matrix, do not do row reduction, please.
You could transpose to row reduction.
You can transpose a new row reduction if that makes you feel better. Yes. So do not use column reduction when you should use row reduction and vice versa. Or you will end up with the wrong answer. Now, if all you care about is dimension, either one works. But if you don't care about dimension, if you do care about the basis elements themselves, for instance, when checking exactness, for instance, when computing homology, care about the basis, then you have to do the correct thing on the row of the column. So, in particular, what does homology involve? Kernel modulo image. You need the actual kernel, not just its dimension. So when you're finding the actual kernel, that's why we row reduce. But you do not row reduce the matrix before. You column reduce that one.
Yeah.
So, let me be really very explicit about this.
And while you're erasing, so analogously, the image is equal to the column space?
Yep.
Okay.
You could think of them as being slightly different, but the notation belies a particular preference. If you think about it as a row space or column space, you're thinking of the matrix, that grid of numbers, as being fundamental. If you're using this notation, kernel and image, then you're thinking of the vector spaces abstractly as being fundamental.
Ah, okay.
So it's a little different in viewpoint.
Right.
So typically you'll see people, as a computer science viewpoint or matrix computation viewpoint, using row space and column space. Whereas you'll see people that are more mathematically centered on, so similarly mathematically sophisticated, but focused more mathematically on the vector spaces. You'll see this notation.
Thank you.
Yeah. Okay, so implications for computation of homology. You okay?
Image decay mod kernel decay plus 1.
Let's see here. So here's k. Here's k minus 1. And here's k plus 1. Here's dk plus 1. Here's dk. So the homology in degree k is the kernel of dk modulo the image of dk plus 1. Is that what you said?
I had the case reversed in my idea.
Okay. Well,
Ascending
Yeah.
versus descending.
ascending versus descending. Homology versus cohomology in some cases, yes. So, yeah, whatever.
We tried that, didn't we?
We did try that. We did try that. It keeps coming up because honestly, I do a lot of sheaf theory, and sheaf theory usually is more natural with cohomology. Not always, but usually. Anyway. All right, so this is the definition of the thing that we want to compute. So typically what we want to do is we want to find out a basis for the kernel. So in doing so, we will row reduce dk.
Because, sorry, you said because.
Because it preserves the kernel.
Okay.
And we will column reduce dk plus 1. Now, this is not the only way to do it. You can row reduce dk and then solve to check to see which of these are in the image of dk plus 1. That also works quite well.
And we column reduce to preserve the image.
Yep, that's right. That's right, because row reducing preserves the kernel, column reducing preserves the image. But generally speaking, if you want the simplest bases around, these are the reductions to perform. Now, in most of your projects, most people row reduced dk and then did the solving, which is a perfectly legitimate and reasonable way to solve the problem. And I think that from a computation on the exam standpoint, the matrices are going to be sufficiently small that either technique will be perfect. Take your pick. Whatever works. Okay. But in either case, do not column reduce dk, do not row reduce the image of dk plus 1. Now, the reason why I sort of hammer this point home is because if you try to compute the homology not of here, but of here, you will need to do the opposite reduction on dk. Bring this up, because homological algebra, like linear algebra, but more so, is about bookkeeping. Please be systematic. Please be organized when you're writing down your computations so that you don't get tangled up in a big knot. Yeah.
So, I was thinking of how we did it for the project compared to how we did it for the homework. For the project, you could like check if the columns of the kernel
Yep.
were in the image.
Yep.
But when we did it in class, we did like method of free coefficients and stuff. Could you still?
Yeah, okay. I see what you're asking.
Could you?
So-
Yeah.
So, all right, so the point is that there's a little bit of a gap here. The gap is I gave you code that performed this for the project, that did this particular row reduction and extracted out and gave you as columns the listing of the kernel. But when doing it by hand, you have to add that extra step. That's a good point. Let's bring that up. I mean, you're asking all the questions when you're driving this, but that's fine. Other people have other questions. Go right ahead.
That's a good question.
It is a good question.
We, you know, there's a lot more stuff that we
there
haven't
sure
gotten
is.
to, so.
I agree. However, this is the sort of thing that is oldest on our agenda. Some balance. If you want to queue up in your brain the next topic you'd like to ask, that would be fine. But, all right, so computing the kernel, let's go into it. Of some matrix L. And that matrix L is right here. So, step one. Step one is row reduce. Once you've got a row reduced matrix, notice the row reduction hasn't changed the kernel at all, so you can still work with it. It's going to be in a particular form. It's got M by N, M rows, N columns, and it's going to have a particular structure.
It's row echelon.
It is a row echelon form. All of this is 0. All of this is not 0. Okay, and so the trick then is you go through and you mark those free rows and free columns. Mark wherever the thing is taken down the step. And those are going to play an important role in choosing your free variables and parameterizing the kernel. So, second step, mark those free variables, and then the third step is figure out free variables after constraining. Or rather, not the free variables, figure out the constrained variables from the free variables. Probably a better way to say that.
Give it the right parameters, you're giving what the general solution is.
Yep. From the free columns. So you pick values for the free columns. You need only find a basis to span them, but that's easy. It could be just 1 and a whole bunch of zeros, and then 0, 1, a whole bunch of zeros, etc. Walk through it however you like. Once you've got that in hand, figure out the rest of the constraints, and you've got your kernel. So that's what we did in class when we were doing this right. Okay.
So that was the method of.
That's the method of free columns. Yep. Standard linear algebraic trick to get a hold of the kernel. And then you can go interrogate that kernel to figure out which of those kernel elements lie in the image of the previous map, however you like. Yeah.
So when we're saying we should row reduce dk to get its kernel,
Yep.
we mean that in the sense of solving a linear system, but is that related to that related to the fact that row reduction preserves the co-image?
Yeah, so the co-image is kind of the other stuff. The co-image are all the non-zero columns.
Oh, okay, so the co-image being, is kind of the complement to the kernel.
Yeah, the orthogonal complement of the kernel, yes.
Orthogonal complement.
Yeah, it's the orthogonal complement of the kernel.
What does that mean to be an orthogonal complement?
So orthogonal complement is every element, so if I have a vector space, I have a subspace. If I have a dot product available to me, then I can define an orthogonal complement to that subspace. It is the set of all vectors that are perpendicular to that subspace.
So the co-image is the orthogonal complement of.
Of the kernel. And theorem, every vector space, if you give me a subspace and I give you the orthogonal complement, list the bases of each, concatenate them, it's the basis for the whole thing. Doesn't actually work for when you leave the comfy world of vector spaces and go into the bigger, wider world of coefficients coming from an arbitrary ring. Interesting.
Arbitrary what?
Arbitrary ring. We're not going there, don't worry. Good. Okay, right, so.
It's an abelian subgroup with multiplication that's associative.
Yeah, all that stuff, all that stuff. The not being able to find multiplicative inverses causes much trouble, is the summary. Okay, other questions or redirection at this point?
Right.
What do people want to hear?
Can we go a little more in detail on induced maps?
Sure. Induced maps, that's a great idea.
And I think I guess also just computing them
Computing this.
explicitly.
Yeah.
Mm-hmm. Sure. Now, I have to admit, I'm going to let you in on a secret. I don't come up with these matrices completely out of nowhere. The way I come up with the matrices is through simplicial homology, because then it's pretty clear what I need to do. So why don't we move on? And then this will, I think, probably will take us through the rest of what we want to talk about, but it'll certainly sweep through all the topics as well. What I'm going to do is write down two simplicial complexes and write down their homology, their simplicial chain complexes, and compute the homology and the induced maps. Okay, here we go. So I need two simplicial complexes. Rather than writing these things out as big lists, I'm just going to draw them. So here is one of them. And when I first started talking about these, I had a map into this space. So if you look in your notes, you'll find a map into this guy.
And we don't have the connection between the back two, right? It's just.
That's right. So this is filled in. This 2 simplex is present. This 2 simplex is not. I will name these A, B, C, D. So A, B, C is included, but B, D, C is not included. And as a result, then the 3 simplex A, B, C, D is also not included.
And AD is not
And AD is not correct.
All right.
So when I first talked about simplicial maps and whatnot, we were talking about dimension preserving simplicial maps, and so as such I was constrained to map into this space. I'm now going to map out of this space, and I'm going to collapse something. I'm going to map this thing into, and just to keep my indices straight, I'm going to name this E, F, and G. Call this map F. And what's going to happen? Well, F of, I'm just going to tell you where F of the various guys goes. So I've got A, B, C, and D. This is X, this is F of X. I'm just going to tell you A maps to F, B maps to F, C maps to E, and D maps to G.
By definition?
I am defining it. So this is a simplicial map by the second definition, rather than the dimension preserving one, which is a little more restrictive. This is the less restrictive definition, telling you where all the vertices go, and the rest of it comes along for the ride. So in particular, AB maps to just the point F. The edge BC maps to EF, or FE. FE. There's sort of kind of reverse. Okay. Now, I do need to orient these things. I do need to give you orientations on these, not because it's necessary, but because it's computationally useful. So I will orient them in the following way. First E, then F. First F, then G. And first E, then G. I'm going to use lexicographic ordering. And A, B, C. So I'm using lexicographic ordering on all of my simplices to set up the orientations. Okay. So that's two simplicial complexes and a simplicial map. Now I'm going to write down the simplicial chain complex for this one, simplicial chain complex for this one, and the simplicial map, and compute everything inside it. Okay. And I got 50 minutes. So let's make that. Okay. So let me label by degree. I've got degree 0, or C0, we could say, that's 0. So C0 of the first one is spanned by, wait, I'm already doing cohomology, gosh. All right, I'm going to start off in dimension, what's my top dimension? It's the largest dimensional simplex I see.
C2.
C2. And then this is going to map into C1, and this is going to map into C0, and C0 is going to map into 0. Descending in dimension. Degree. Okay. So the degree follows the dimension, and it goes down.
So you start off with R1.
That's right. I've got just one. Just one 2 simplex. Now down here, I don't have any. Now over here, how many edges do I have in the top diagram?
5.
5. How many edges do I have here?
3.
Good, I can count 2. It's not over yet. And here I've got 4. Okay? So, now, again, it is important to be organized. So to be organized, well, what we should do is we should label the simplices. I'm going to label the simplices again using lexicographic ordering so I don't mess myself up too badly. So not only am I using the lexicographic ordering for the orientation, I'm going to use it as well to tell me what basis element is which. Okay, so this maps ABCD to which simplices? The which edges, the 5 edges that I get mapped to are the, the various 1 simplices. So I'm going to map ABCD, or ABC rather, into AB, then AC, then BC, then BD, and then CD. Those are the 5 edges. That is a 5 by 1 matrix. Now, this map, I'll fill in the entries in a moment. This one is going to be labeled with the rows of this one or the columns of this one. AB, AC, BC, BD, and CD. And my 4 simplices, A, B, C, and D. Down here, I don't have anything here, so I've only got something going on over here. Again, lexicographic ordering on them. I've got EF, I've got EG, and I've got FG, and EFG. Now, as far as the chain maps are concerned, this one clearly has to be the 0 map, and that's all there is to it. And I've got 2 more maps that I need to define.
3 by 5.
3 by 5, this is going to take me into EF, EG, FG on the output. That is the column labels here, notice they match up. The row labels are all of these guys. Oops, I didn't leave myself enough space. B, A, C, B, C, B, D, C, D. And here I have a 3x4, E, F, G, and this is A, B, C, D. Okay, now I get to fill in everything. Now the chain map, component maps, the vertical arrows are easy to fill out. You fill out a 1 if it works, and a 0 otherwise. But be watchful of orientation. If you flip the orientation, you should throw in a minus sign. Okay, so here we go. On this side, there's no orientation to worry about. They're just vertices. So what goes where?
A goes to F.
A goes to F. B goes to also F. C goes to
E.
And D goes to G. Okay, that's that. Now what about AB? AB goes to F. So AB doesn't go anywhere. What about AC? AC goes to FE. That's the opposite of EF. What about BC? BC goes to, again, the opposite of that. BD,
Goes to FG.
FG, and CD, EG. Okay, not so hard to write those out. Now what about ABC? Well, we get our sign from the entry we delete.
So that'd be a 1.
0, 1, yeah, plus 1, minus 1, plus 1, yeah, plus 1, minus 1, plus 1, 0, and 0. Okay?
This is all by that formula, right?
Yep.
Wait,
Did I do that wrong?
Why is it that there's only one column?
There's only one column because I only have one two-dimensional simplex going from R1. That's telling me how many columns, it's telling me how many rows.
Oh, so why do we have to specify what it does with every single edge if there's only one option?
Well, because we're essentially telling you that the 3 edges that participate in this two-simplex are these 3 and not these 2.
Okay, fair enough.
All right? So moving right along, if I've got an A, that's a minus 1, plus 1, 0, 0. This one here, this AC, that's a minus 1, 0, plus 1, 0. BC, that's 0, minus 1, plus 1, 0. BD, 0, minus 1, 0, plus 1. CD is 0, 0, minus 1, plus 1. And we got one more of these to fill out. Minus 1, plus 1, 0. EG is minus 1, 0, plus 1, 0, minus 1, and plus 1. All right. Yeah.
For the chain maps, do you get negative ones because when you do, it's an opposite arrow?
Yep. Orientation flip. Yep. Again, lexicographic ordering everywhere in sight will help you avoid minus sign problems.
So even if you're doing this in research, it's all lexicographical?
No.
Or I mean, those would be determined by theory?
Choose the ordering, then stick with it. When you were doing things on the board, you take the extra risk of making a fool of yourself. So I take extra precautions.
Okay.
Can you briefly state the thing with the rule of the minus signs?
Okay, so the rule of the minus signs is to go from a K simplex to a K minus 1 simplex. I delete a vertex. Alternate the signs of the vertex that you delete. We've been starting in this class, starting with a minus 1. Minus 1 plus 1, minus 1 plus 1. No, I got it backwards. We've been starting with a plus 1, plus 1. Negative 1 to the 0. We've been using Python, we've been indexing starting with 0.
Yeah.
If I had been doing this in MATLAB, I would have been the other way around. And unfortunately, half of my life is in MATLAB, the other half is in Python, and I always mess this up.
You can always just add 1 to your index.
Well,
So we're
yeah.
starting at -1. H2 is zero.
Again, it doesn't matter.
Yeah.
Zero slots.
Doesn't matter, so long as you're consistent. Again, I'm trying to mitigate screwing up the board. Okay, right, so, now, the question was how to compute homology of this thing and how to compute the induced map. Now, interpretation of homology is telling me what? Well, the homology here really is in dimension 2, it's about bubbles. Are there any bubbles here? If I were to imagine this as being a space that I filled in, does it look like any
Yes.
bubbles? Can you inflate this?
No.
No, it's flat. It's a flat little thing with a little loop attached to it.
Okay.
Non-inflatable. So there's no homology in dimension 0, that's basically what that means. Now, the set in dimension 1, it's about loops. Could you catch it? Basically, the homology in dimension 0 says, can I catch it by wrapping it around something? Wrapping it around a point, a two-dimensional surface. Here, so the answer is no. Here, can I catch it by wrapping it around a one-dimensional surface? A string. Yeah, I could thread this on a string. As I could thread this guy on a string. This is a loop that loops around my little thread. If I looped this around a string, I'd have a little bead on a string. This would be a differently shaped bead, but nevertheless a bead. So there is some one-dimensional homology. And then can I move around, can I separate the pieces by threading a point in and amongst them? Well, no. So one connected components in both cases. So in both cases, intuitively, dimension of H2, 0. Dimension of H1 is 1. Dimension of H0 is 1. So, good cross-check. These dimensions are called Betti numbers. These are the Betti numbers. I mentioned that in the last class. Actually, interestingly enough, the Betti numbers were the first thing that was studied in algebraic topology, were these Betti numbers. Okay, so, and you can kind of intuit that and use that as a cross-check. Now, if you take a look at the kernel of this map, what is the kernel of this map?
Span up into
Yeah, 1, 2, 1, exactly.
1, 2, 1, 0, 0.
I don't know if it's right.
Oh, no, wait.
No. This map has no kernel. It's trivial structure.
Trivial.
Trivial kernel.
Because there's one pivot.
Trivial kernel modulo, whatever image, 0 image, still 0, hence dimension equals 2. Now what about this one? The intuition here is that this, both at the top and the bottom, are going to have dimension of h1 equals 1. Can we guess an element of the kernel that's outside that image? Well, we can do our row reduction game here, and well, we don't have to do any column reduction. So we just do a little row reduction here, and we can figure out what's inside the kernel of this that's outside that. So let's go ahead and do it. Let me row reduce.
-1, 0, -1, 0, 1. Wouldn't that be in outside of it?
Remember what I said about mitigating errors at the board. Hold on a sec. I'm adding these two guys, and now this is 0, 1, 1, 0, -1, 0, 0, 0, 1, 1. I'm going to add these two guys in place. So if I add those two guys, I will get 0, 0, -1. And I'm going to add these two guys. Okay, all right, so I've row reduced. Okay, let's go find my little bit here of here. And let's see, let me mark my columns accordingly. So let's see here, I have, let's see here, third and fifth columns are marked. So what is the dimension of the kernel of this matrix? 2. Dimension of the kernel of this matrix is 2. And what are they spanned by? Now you can say your bit, now that I'm ready for you.
What?
So someone had told me the kernel of the matrix by inspection, and I was not smart enough to be able to catch that.
Well, It's the span of the.
Well, okay, fine, whatever. So, all right, so look, I need space to write it. I'm gonna write the transpose of it up here. I got two of them. One of them is gonna be here, and I've got a something, something, 1, something, 0, and I've got a something, something, 0, something, 1. What are the somethings that I need to put in there? What? What are the somethings that I need to do? Because I'm filling in this free column with a 1 and this free column with a 0.
The thing in red is the kernel.
And the thing in the red is going to be in the kernel of this matrix. Oh, each row is going to be in the kernel of the matrix. I've run out of room. Well,
Oh, right.
1, -1, 1, 0,
Oh.
0.
1, -1, 1, 0, 0. And then the next one is?
Haven't gotten there yet.
Okay. No
It's
problem.
hard to do sideways.
I know it's hard to do sideways. Turn your head. I can do it.
So -1, 1, 0.
How about that
Oh, really?
one? Nope, I'm
No.
wrong. I'm wrong. I'm wrong. I'm wrong.
0, 0, 1, 0, -1, -1, 0.
-1,
0,
1,
1,
0,
0,
-1, 1.
-1.
1, 0, -1, 1.
Okay. Now,
Where is that from?
So-
So you pick one, and then you
That's
say,
it.
okay, this
Verify
needs to
that
be
that
0,
works.
so you stick that in there, and you, okay, this is 0,
So
so
what's
that's
the name for
gonna,
that though? What's the,
finding the kernel.
finding the kernel.
It's, you're just doing systems of equations.
Yeah, you're just doing systems of
Piece
equations.
by piece.
Did we do that right? Yes. Yes, indeed we did. Okay, now, where do these guys map? Well, first of all, let's now come back over to the diagram here, and let me draw them. Let me draw them. What's the first one? The first one is AB with a plus sign. What's the second one? AC with a minus sign. Opposite the orientation that I've got going on there. And what's the last one? BC with a plus sign. Follow the BC. So that's the first element of the kernel. The second element of the kernel is the first AB with a minus sign, then AC with a plus sign. What about not BC, then BD with a minus, and CD with a plus. So those are the two elements of the kernel. Now, look at this. What is the image? The image is this first one. The image of this map is that one. So that's this loop. And it says this loop has been collapsed by that simplex. Now, if we to finish off your question about the induced map, now what we do is we follow. So this is not in the homology. This is. Now, to find what the induced map does, you take each one of the elements of your homology, multiply it by this matrix. So, row into, well, column, sorry. And what is that? It's going to be in terms of the E, F, E, G, F, G. Row into column, and what do I get? Well, 0, -1, 0, and that's it. So just -1. So negative EF. What's the next thing that I get? Row into column here, and I get a positive EG and an FG. What happens to there? I get a negative FG. So the induced map, multiply this matrix by this is supposed to be a column. And I get -1, +1, -1. That's the output. So this guy, mapping through here, has given me this. When you look at it over here, now let's read it off. Negative EF, positive EG, negative FG. So what it's saying is it's saying that this loop, oriented in this way, has been mapped to this loop, oriented in this way. And that's what the induced map does. So,
So our induced map would be that column vector right
Yep.
there, and that's it?
well, the induced map is the listing of these columns for each of the columns over here. Yes.
So if we were, for example, if we had two
Two elements of the
two
kernel.
elements of the kernel, we could return, in this, for example, a 3x2,
Yes.
and that would be perfectly all right?
Yep.
All right, okay.
Yep. So, for Evan's question, he said, could I say the statement again? I'm taking one of these loops here. Which loop? Well, the one that is generating H1. This one here is 0 in H1. So I take the non-zero guy, the non-trivial guy, where does it go? It took this loop, oriented in this way, and mapped it to this loop, oriented in this way. So the induced map takes loops to loops, non-trivial, topologically interesting loops, to other non-trivial, topologically interesting loops. Or at least to other topologically interesting loops. They could have got mapped to 0. Take 0, in fact, look, 0 gets mapped to where?
0.
It gets mapped to just basically sitting on F. F is a 0 element in that homology. It doesn't even show up. Okay. Yeah.
So because we're thinking of A, B, C, D, E, F, G as all being vectors, they could all be thought of as being vectors, right?
A, B, C, well, where?
Like just kind of in simplicial homology.
There, okay, A, B, C, D, thought of as vectors is specifically right here.
Right, yeah.
Yes.
So then when you're taking loops to loops in the induced map,
Right.
you think of that as
Connected components to connected components at this dimension. Here they're connected components to connected components. Here they're loops to loops. Here they're bubbles to bubbles. Here they're, three-dimensional voids to three-dimensional voids, etc. Three-dimensional spheres, actually.
and the connected components are two-dimensional.
No, the connected components are the degree 0 guys. These are the maximally connected chunks. So if I take a look at it, all right, so let's. I don't want to go into this.
Okay.
We'll run out of time here, but
Already ran out.
yeah, we've already run out of time. So I think this is probably. I mean, this is a nice example. It's probably good to stop there.
I mean, I'll stay, I wasn't saying,
No,
no, I'm just.
No, that's fine. No. Did you grab that camera?
Oh, yes.
Thanks.